An equation is said to be quadratic if it can be written in the form ax squared plus bx plus c is equal to 0. The values a, b, and c are real numbers, but the a value, which is the leading coefficient, cannot be 0. We do need to have this term present in order to be considered a quadratic equation. We need to have that x squared term. So in this example, we're asked to determine whether or not the equations are quadratic. This first one can be written in that form. If we were to distribute the x into the parentheses, we're going to get x squared minus 4x is equal to 3x plus 2. If we were to subtract 3x and subtract 2 from both sides, we would see that this equation then can be written as x squared minus 7x minus 2 is equal to 0, which does fit the required format for a quadratic equation. Now, ideally, we don't have to go through all of that to determine whether or not it's quadratic. We should be able to just look at it and see, well, if I were to distribute that in, do I get that x squared term that's required? And we would in this case. So even if we didn't go through all these steps, we could still see that, yes, this is a quadratic equation. Now, notice also in the general form of a quadratic, we do not have any x's in the denominator of a fraction. So in part B, because there's an x here in the denominator, that says that this is not quadratic. As a matter of fact, it's rational. We do see that we have that required x squared term, but because we have an x in the denominator of a fraction, it says it's not quadratic. And similarly in part C, we see that we do have the x squared term, but it's under a radical. We can't have any x's under a radical. We can't have any x's in the denominator. As a matter of fact, a quadratic is also what we call a second-degree polynomial. And so this equation down here in part C is also not quadratic. We would call that one a radical equation.